I'd like to thank everyone who is joining us today. Welcome to today's CNCF webinar, Hardware for Kubernetes, Peeling Back the Layers. I'm Jerry Found, and I'll be moderating today's webinar. We would like to welcome our presenter today, Eric Riedel, SVP of Compute and Storage Solutions at IT Renew. Just a few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your questions in there, and we'll get to as many as we can at the end. This is an official webinar of the CNCF, and as such, is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of the Code of Conduct. Please be respectful of all your fellow participants and presenters. Please note that the recording and slides will be posted later today to the CNCF webinar page at cncf.io/webinars. With that, I'll hand it over to Eric to kick off today's presentation.
Thanks so much, Jerry. And thanks everyone attending for giving up a part of your day to listen to me today in this the CNCF webinar. So as Jerry said, so I'm going to talk a little bit about the hardware underlying Kubernetes, so the infrastructure that many of us depend on. I'm hoping to bring up some topics that aren't maybe a natural or everyday discussion for many of you. So I and our teams at IT Renew worry about these things, maybe so others don't have to. But we thought it might be worthwhile to peel back some of the layers, as it were. So very briefly, IT Renew. So I work for a company called IT Renew. I've been here a little over a year. The company is headquartered in Silicon Valley. We've been in business a little over 18 years. And the primary business of the company is decommissioning of data center equipment. But as part of that, we've been involved for the last 10 years, 8 to 10 years, with almost all of the largest service providers in the US. And working with them on designing the systems that go into their data centers, as well as helping them when it's time to decommission some of that hardware. I'm with a product division called Sesame by IT Renew. That's about 2 years old, and we're repurposing some of that equipment into rack scale open compute solutions. I'm not going to talk in great detail about IT Renew, but this idea of the circular economy, circular data center will come up again a little bit later if we have time. Well, what I do want to talk about today, so what brought you here, this is the abstract of the webinar. And so what I want to do is look under the covers a bit, or peeling back the layers, as we put here, to what lies underneath the infrastructure that we all work on every day, right? Whether we're developing applications or infrastructure for the cloud, or whether we're just using the cloud. At the end of the day, there are servers underneath serverless, and hardware underneath kind of all the software in the world. And I thought it might be instructive, or we thought it might be instructive to give some sense of how that those systems are developed, where innovation is coming from, and how open hardware applies just as analogously as open software. So we're going to go into a bit of detail and give some examples, right? But it's really just a flavor. The subtext of my talk, so the layers, when I thought of layers, I thought of onions, and the subtext I wanted to put in the abstract was I'm going to tell stories about designing hardware until everybody cries, but they wouldn't let me put that in. So we're just going to proceed through some layers, but I am going to tell some stories. I'm going to start with this idea of open and how it applies to hardware design, specifically something called the Open Compute Initiative. I'll go into some details. Then we'll talk about some of the changes that have taken place over the last 10 years that created cloud native, and how that applies to what we're doing in the infrastructure layers. And then I'll start to peel back some layers and dig in. So I'll show you a little bit of what happens inside of a server. If we have time, I'll talk about this circularity that we're enabling at IT Renew, and then just talk about some of the views of what has changed in computing in at least the 20 years that I've been doing it. There are additional stories that, because of the 40-minute format, I will spare you. I've given these talks before at LinuxCon and other various events. talking about disks and what happens if you suddenly have to respond to updating 50,000 or 75,000 disks that are in 10,000 data centers around the world. BIOS updates, networking, physical, virtual. So suffice it to say, I have a lot more stories than I fit into this this webinar. Some of them make you cry. Maybe some of them also make you smile. So the first aspect I want to talk about is open, right? And what we've found in our current work, kind of at ITR, but also kind of in my work over the last many years in computer systems design, I probably spent 15 years involved in the Linux community one way or another, is that that open is necessary but not sufficient. So I think it's pretty understood that without openness and the collaboration of the open community, we wouldn't be where we are today in computing, and certainly not in large scale computing. But there's a lot of pieces underneath that, and I just want to make sure that give people a background appreciation for those. So so starting with the hardware, right? So there's a lot of component pieces that go into building the infrastructure under which all of our data centers operate. And I'll dig into some of that later. What's super important to remember is that there is deep design expertise, engineering expertise in hundreds, if not thousands of areas, right? Individual, material science, chemical engineering, electrical engineering, drive design, enclosure design, et cetera. We're dealing with a significantly wide range of engineering disciplines, and we're depending on everyone within those disciplines to apply engineering techniques and a commitment to design integrity, design quality, and production quality, right? I spent 7 years working at Seagate. At the time, Seagate was producing one disk drive every 3 seconds, right, in order to satisfy the global demand for storage. I'm sure that those numbers are larger today. And if you think about how many chips are being produced and fabricated every second, it's significant numbers, right? And all of that requires significant engineering diligence, right? Whether it's being done in the open or not, right? Open gives leverage, but the base is engineering expertise, right? And the same is true in software, right? There's also rigorous design techniques, design reviews, code reviews, integration pipelines, et cetera, ways that we've become much better than we were 10 years ago, 20 years ago in engineering software in many of the same ways that we engineer hardware. So this, in my experience, operating at all the layers of this system, or both layers back and forth, that there really is much more of a continuum than there was, right? But what that also has led to is a huge breadth in a dynamic range in the skill sets that are needed, right? And the way I often talk about this is from capacitors to the cap theorem, right? So at one end, we're literally talking about electronic components, electrical components, and how they behave, and the materials that go into them. And at the other end, we're talking about concepts of theoretical computing, algorithmic design, and so on, right? So capacitors to the cap theorem. And in addition, there's a range of additional disciplines that maybe weren't as appreciated as computing and computer science in user interface design, in user experience, in the way that humans interact with our systems, right? So ideas like cognitive load and those types of interaction experiences are also relevant, right? The important thing is there's a huge dynamic range of expertise that is applied to those problems, right? And that expertise, that range of expertise is also present in my own engineering team. So my engineering team, we have electrical engineers learning literally about capacitors and heat exchange, all the way to software engineers worried about code in Git and repositories and so on, right? So a huge dynamic range. The other change that is probably unique to the last 5 years, maybe 10 years, but certainly 5 years, is the much more extensive collaboration that we generically refer to as DevOps between the people who create the technology and the people who are operating the technology day to day, right? So certainly when I first started operating in computing, the idea was that we were going to design our software, even design our hardware, and then put it out in the world to be sold, bought by other people, and then eventually down the line, 3, 4, 5 levels of indirection used by someone else, deployed and used by someone else. And that's no longer the case today. What we've done is really reduce that feedback loop. So that there is a much deeper collaboration between the folks who are using the systems day to day, operating them, and the folks who are designing the systems. And that means that appreciation has had to grow in both directions, right? That the designers have had to focus on how will this technology actually be used in practice, and the practitioners have had to focus and learn a bit more, peel back some layers, if you will, on how the technology is built in the first place in order to understand how it works, right? And again, all of these characteristics apply in how teams operate and how individuals operate, really independent of whether it's open source or not open source, right? And then the final piece of this, in the world that we operate in today, we just wouldn't be efficient. We wouldn't be able to do hyperscale computing if we didn't have the machines doing most of the work, right? Meaning the automation and the analytics and the machine learning, for lack of a better umbrella term, that we use to have the machines manage the machines, right? That what we used to do manually even a few years ago simply can't be done manually at this scale, right? So we've leaned heavily on the machines, right? So these are kind of 5 areas of backdrop as I go through some of the stories. All right, so let me talk a little bit about open hardware. So I want to introduce a community that maybe some folks on the phone are familiar with, but I presume some folks haven't heard much about. Something called the Open Compute Project. This is a list of the member companies of Open Compute with a very wide dynamic range of the types of technologies that are present in your data centers today, right? There's companies in here that design sheet metal for racks. There's companies that design chips of all kinds, right? All kinds of flavors and sizes and so on, chips. And cables and connectors, right? But there are also a significant number of end user companies that are really traditionally consumers of this technology. So you see Goldman Sachs, Facebook, AT&T, Deutsche Telekom perhaps. And what's important in the OCP community is that those companies feel like they are part of the design process as much as they are consumers. So we've really collapsed some of that interaction, and that's been possible because we've done it in the open, right? So this is kind of a short history of the Open Compute Project. Was started in 2011, so just under 10 years ago. I wasn't at the first meeting, but I was at the second meeting in New York City. That's where that picture is from. And there was a lot of philosophical points of, hey, hardware is mysterious. It's it's done in the back rooms. It's done with NDAs and bilateral relationships, and there's a lot of complexity, but also a lot of stuff is hidden from the world. And Open Compute set out to dispel that, to create a community where we collaborate together, right? And as you see in the table, this was a great growth at the beginning, right? So from the event in New York to San Antonio to Santa Clara, kind of doubled the attendance each time, and then almost tripled to when the first event. But more important than that, it was then a steady commitment from members for the next 7 years, right? So that commitment has remained. So this wasn't just, hey, let's talk about it, let's learn something about data centers, and we'll talk about it some. This has been a sustained effort for more than 9 years at this point, right? Continually growing, right? And then what you see in the bottom task is, I think, something that you'll recognize also next week at KubeCon, I hope, is that by changing the event from physical to virtual by necessity this year, so we postponed the event from March to May in order to deal with the new kind of virtual approach, but we more than doubled the number of attendees and more than tripled the number of companies that participated, right? And this is great news for those of us looking at the richness of this community, because it showed that there were some barriers to physically, people flying to Silicon Valley to have these discussions. And by opening this up in the virtual world, we were able to draw a much more significant audience, right? And I'm hoping that, that folks will be able to see this next week in KubeCon as well. The other good news for some of us, so we also use the same Entrada platform that's going to be used for KubeCon next week at OCP. So, we've also seen the technology of the platform operate. So we'll be interested to see others' feedback, right? But our experience was very positive, right? And that's also matters, one of the logos at the top is this OCP community, because OCP isn't just this kind of headline event that takes place every year. There's also been some regional events in Europe and Asia, but it's an ongoing commitment to projects, right? And that's what, I moved my mouse. And that's what I've shown here. So there's several categories in which we divide the projects, but there's also several hundred projects. So what you see, the numbers here refer to the number of projects in each category. And it shows the dynamic range of what's discussed in these committees. So there are literally groups that look at data center facilities. So the concrete and the sheet metal of building a data center, designing a data center to have a low PUE, high efficiency in the equipment that's stored, being able to put thousands, tens of thousands, maybe millions of machines and do it most efficiently, cost effectively. There is rack and power design, which I'll go into a little bit more, and any number of networking and server design projects where we're working collaboratively across the industry. And there's great power in that collaboration. So I've been involved in hardware projects for almost 20 years, sometimes with several companies in an NDA, occasionally a standards committee. But what we've been able to do effectively here in OCP across, like I say, hundreds of projects is get a dozen, maybe, or half a dozen, maybe sometimes 20 companies, 25, 30 engineers together to address a small subset of a problem, right? And that gives a richness of experience and a richness of interaction that simply isn't possible when you have 2 or 3 companies operating in NDA type of rooms, right? So we're convinced, and the truth of this technology, the impact of this technology shows that we've gotten great benefits of that. A very brief shout out. So OCP is going to do a tech week in November. So when you look at the slides, you can click through to that. And the virtual summit in May was actually free to register, and all of the material, all the talks, all the keynotes, all the discussions are available still for 11 months after the event. So you can follow this link and listen to some of those talks and some of those projects discussed, right? So mention that to others in your company, or maybe yourselves who are kind of interested in more depth than what I'm going to talk about here. So in order to summarize the impact or the benefits of open hardware as we experience it, as I see it in my day-to-day, right? We're able to have more flexibility, right? Because we're operating in the open. There have always been standards, right? We've had standards committees since the early days of computing, right? Sometimes those were also in darker rooms or rooms of various shades of darkness, and there were political agendas and so on. There's certainly agendas in some of the open projects as well. But the ability to do those interactions and create those designs in the open, contribute them to the community, leads to a much wider range of flexibility of things that work together, that we know will work together because they were designed in the same context, in the same community. Right? So there's absolutely more flexibility. Of course, the holy grail, or the point of much of this effort, is increasing the density of computing. So higher density computing, meaning that we can fit more storage, more servers, more networking connectivity in less space, right? And by doing it in less space, more efficient power, which is the next point, saves cost, and more importantly, allows us to address more of the demands of software everywhere for sophistication and additional kind of compute power, storage capacity, right? It has never been the case in the last 20 years, at least, that I've been in computing, where there wasn't a demand for more cycles and more capacity, right? Whether you're talking about Moore's law for transistors, or Kreider's law for storage bytes, there has always been, and continues to be to this day, an insatiable demand for compute cycles. So the more efficiently we can deliver them, the better, all right? We spend a lot of time thinking about rack level power optimization, right? Because we have to feed, so in order to make all this computing work, we have to feed in electrons. And the less electrons we feed for a given amount of work, the more efficient the whole process is, right? The lower the carbon footprint, or for the same footprint, the more results we can achieve, right? So that's very important. And one of the great things that we've seen as a side effect of designing for power optimization and for simplicity is we end up with systems that are more efficient, cost less because there's less components, there's less complexity, and there's fewer points of failure because there's less components and there's less complexity. So we've made things simpler, which means they consume less power, they cost less, and there's fewer points of failure. Right? So self-fulfilling in some ways, or multiple benefits from the same optimization goal, right? Optimized cooling, very briefly, right? It turns out, every electron that you put into a piece of electronics will exhaust as heat from that electronics, one way or the other. And so that means that there have to be additional electrons that you spend removing the heat that the earlier electrons cause. And it should be obvious, that's completely wasteful, right? So the more electrons you have to throw in after the initial electrons just to cool the systems so that they don't melt and they'll continue to work tomorrow, is an overhead that if we can ameliorate it another way, we can deal with. Right? And then finally, kind of streamline maintenance, right? And that also very nicely tags in with that idea of less components lead to less cost, also lead to easier maintenance. Right? And then I'm not going to repeat everything again, but we believe that those same kind of analogous wins are benefits of open software, right? And it's standards in the software layer, right? You talk about them as APIs instead of standards. High density computing, really fitting more algorithms into a particular silicon inch, right? Power here, I've been a little bit generous, so I use power to mean functionality, right? More features, a wider set of features in different software stacks. And cooling, there's no obvious analogy for cooling software, so I changed this one to validation. But the idea of continuous integration, CI/CD pipelines lead to that finding errors before they get out into the field. And in many cases, if you're doing modular systems, modular interconnectivity, you have fewer points of failure, right? And streamline maintenance the same as in hardware, right? And then just to remind people, right, I showed a bunch of logos for open hardware. And if you think our committees are complicated, this is only a fraction of the CNCF landscape. And so, of course, the richness of software is an order of magnitude wider than it is in hardware. But hopefully I've motivated that we're using some of the same types of techniques and processes, right? Okay, so that's kind of the first kind of major point I want to make. Kind of open compute, very analogous to open software. So now, how do we match the infrastructure to the hardware, right? And so the story I want to tell here is I want to go back also 10 years. So at the same time as I was going to those early open compute meetings, I was with EMC at the time, and we were talking to our customers about the early days of cloud and what became cloud native, right? And what we were looking at was two significant trends that we, because we're EMC, we cared about the data, so we matched those trends to this underlying data infrastructure. But the true trends that we were looking at was the success, ambiguous kind of success of virtualization. And what virtualization had done is it had put legacy application stacks into manageable packages, right? So virtual machines were now encapsulations of a particular functional stack that before had to live on some purpose-built hardware, right? We built some hardware, we built application on top of it, and then that ran the user level functionality, right? And then if you needed a different application, you built a different infrastructure and you built a different stack, right? Virtualization allowed us to stick that all into a box, if you will, container, a virtual machine, and then deploy those flexibly, right? Most importantly, you could do replication. So if you had one of those boxes that could support 1,000 users and you suddenly needed to support 2,000 users, you simply created a replica. You create another copy of that to serve those other users. If you needed 10,000 users, you created 8 more, right? Wasn't always exactly that easy, but a lot of times it was, right? Or if you needed to move them around your infrastructure, migration could be done, right? So that was one significant change in the way that applications interacted with systems. But the other one is what's now become referred to as cloud native. So with EMC, we were heavily involved with VMware in the early days of what became Cloud Foundry, right? And the premise for Cloud Foundry at the time was, hey, don't worry about all the low level, all the packages that need to be installed and operating systems and so on. Developers just want to worry about connecting together the modules of their application, the droplets they were called in the early Cloud Foundry, and then you don't have to worry about the plumbing, as it says in this marketing, right? The infrastructure, right? And that is what became cloud native computing, right? So applications that were designed from the beginning to not worry about the infrastructure, right? The applications, legacy applications that we had to stuff into virtual machines was because they were making system calls and they cared about the kernel APIs and so on. That's why we had to stuff them into virtual machines. But these cloud native, what's now cloud native apps were built with an independence from the infrastructure in mind, right? And then at the same time, we had other frameworks such as Hadoop, for example. So at the time, EMC had just bought a company called Greenplum that had a Hadoop distribution. So we had other ways of expressing application semantics at a higher level than at the individual packages and code and database lines. And then the final piece that we brought kind of from EMC, because it was our kind of view on the world or what our customers expected from us, was there was a common layer of data that underpin both of those, right? So that would be what our premise was, that would be the most powerful for the customer, is if the customer had their satellite data or their imagery data or their customer information, and they were able to apply these different kinds of applications developed in different paradigms to the same underlying data source, right? That's what this diagram was. And most importantly, it led to kind of this diagram, which was kind of in the early days of cloud, again, a presentation from 2012, where we were going to take individually developed stacks, hardware and operating system and app, and instead of having them each be individual silos, we would have a pool. So what we now think of as a fleet of computers, a hyperscale fleet, and then we would float these applications on a nice fluffy cloud above that equipment, right? And then you could design the equipment independently of those applications. And we needed the plumbers and mechanics of various kinds to operate in that intermediate layer. but we were able to achieve that separation, right? And in very much in 2012, this was speculative, right? But fast forward to today, right? 8 years later, maybe 10 years, and we've achieved those goals, right? And it's illustrated in this kind of very busy set of artwork. But we've taken the advances in agile development, the cultural change that came from iterative development, customer interaction, heavy customer interaction, right? We built the clouds in the sky. We built these cloud cities in the sky, sometimes by putting additional wiring, right? Power, network wiring, physical infrastructure in place. But we've built this idea that we can float the application. And in the application world, there are now any number of software stacks, application frameworks, user interface frameworks, AI, machine learning frameworks. So different software stacks that can be applied and created and combined in delicious ways. And they can float on that infrastructure, right? So we've achieved what in 2012 was just a vision, right? And of course, behind it is all the great logos of CNCF, right? So this was a significant change. We're all aware of this change, right? But how does this impact the infrastructure? And the good news is that separation that we were looking for to kind of hide the complexity of what we have to do under the covers has also been realized, right? So that specialization and that modularization is very much the reality today. And that's why we can independently pursue the infrastructure and let the applications and the ecosystem run above and worry about just the places where they interact and not about the end-to-end, right? So let's peel back a little bit on infrastructure. So the good news is a lot of that boils down to threads and containers, right? And so let's take a look at hardware. I promised I'd eventually get to some hardware. So here are 3 servers from our portfolio, right? And the 2 biggest characteristics of these servers is that we can host threads. So we have physical cores. So the machine at the top has two big heat sinks. So that means 2 processors underneath. Each one of those is a 16-core physical processor. So 32 physical cores, 64 virtual cores to run, at a minimum 64 threads at once. And with multiplexing, of course, there's thousands of threads active in one way or another. Then the smaller machine in the center is an 18-core, and the very smallest machine at the bottom is a 16-core, right? And then so there's any number of threads that can be loaded onto these machines. What about the containers? So the containers in this analogy are loaded into the memory. So you have the memory modules. So the top server has 4 banks of memory, 2 for each CPU. The one in the center, 2 banks, and the one at the bottom, 1 bank of DIMMs, so 4 DIMMs to support that 1 CPU. So we've got from 0.5 terabyte of memory at the top, 1/4 terabyte in the center, and 128 gig in the bottom. By our estimate, right, a 512 gigabyte machine, depending on what you're trying to do, anywhere from 50 to 100 containers should be able to fit into that memory, and they can be active with the number of necessary threads, right? And then in addition, on the side, on the right-hand side, you also see, for someone who's spent a little bit of time with servers, there's also kind of networking and storage. I won't get into a lot today, but those are also kind of connectivity in each of these servers. Right. But a lot of folks aren't interested, or most folks aren't interested in just single servers, right? You don't want a single container or a single small number of containers. You want a whole port full of containers, or a whole fleet of ships carrying containers, right? And so that's precisely what we do in the hardware space. So we integrate these servers. So these are 4 open compute designed racks with a total of 160 nodes. So they have 160 motherboards like that first one that I showed in the picture, 5,000 physical cores, 10,000 threads. So in principle, the system can be doing 10,000 things at once. And with the speed of multiprocessing, it easily, to a human, it looks like it's doing 100,000 or 1,000,000 things at once, even though at some physical level, it really is just 10,000 things. And even that last factor of 2 is a little bit of a cheat. So 5,000 things, right? But it's a lot. And then similarly, containers, right? Sorry, political call. And so the memory, so this collective system, 80 terabytes of memory. So 8,000, 10,000, 16,000 containers that could live on this collection of hardware, right? So that's what we're building. So that's at the end of the day what data centers consist of, right? Is hundreds and hundreds, thousands of these types of racks of equipment, right? So I promised some more onion cutting. So when we take another closer look at some of these servers, right? So this is a close-up view of 2 sets of equipment from our current product line from the OCP portfolio. And I want to just do a little bit of side-by-side and peel back another layer, look inside of the servers. So here, this is a traditional kind of 1U pizza box server. The reason we call them pizza boxes, they're stacked literally like pizza boxes. So imagine 40 of these units stacked. Imagine that they're coming out of the screen towards you. But what we actually do is stack them in racks like I showed you. And then next to it is an OCP designed node, right? So you see kind of some plastic covering rather than the sheet metal. So already taken some savings there. But if we peel back the layer, the covers, right, we see that on the inside, it's actually very similar, right? So the electronics, quite similar. There's 2 heat sinks in the OCP node. They're located front to back. In the 1U server, they're side by side. But underneath those heat sinks are similar CPU cores. So basically the exact same CPUs are compatible with both of those systems, right? Then we have the memory, so that's where the threads are, right? We have the memory to hold the containers. 12 DIMM slots in the 1U server, 16 slots in the 2U server, but that's really just a matter of space. Organized on both sides of the CPU complex. Because the distance to memory, right? We want to minimize the length of cabling or the length of traversal that the electrons have to do in moving between the CPUs and the memory, right? But then if we take a bit of a closer look, right? What we also see in the 1U server is there are, it looks like 6, but it's actually 12 individual small fans that are responsible for moving air through the system. And this is one of the first areas of innovation that OCP kind of attacked, is the premise of 1U compatible computing was that you needed to be able to mix servers from different vendors. So you'd have a Dell server in 1U and an IBM server above it and an HP server above that. And so there were normalizations within this U concept, right? And so that means that these tiny little fans here in the middle of the 1U server needed to take care of all the airflow for that server, because there was going to be a server above and a server below, or importantly, 19 servers above and 20 servers below in a 40U rack. And these little fans needed to take care of all the airflow for the CPU complex, for these drives in the front, for the I/O boards in the back, because there was no other place air was gonna come from, right? So the air had to be pulled from the front of the system to the back by these little fans. And because the fans were super important, there also had to be redundancy. So that's why each of these modules here is actually 2 tiny little fans together, right? And when the OCP crew looked at this, and when you look at this kind of thermodynamically, this is one of the worst ways that you can do this, because a tiny little 1U fan moves a very small amount of air, right? There have to be 6 of them in order to move air across the entire chassis, right? And there have to be a pair so that one of them can fail and the other one can still continue to move air, right? And so what was done in the comparable OCP design is they expanded to 2U, and I'll explain why that made sense in a moment with a different picture. But we made the servers 2U tall, which allowed the fans are now 2-inch fans or 2U diameter fans, which means they move proportionally more air than the tiny little fans. And we still have 2 fans, so there's still redundancy. If one of the fans fails, the other one is still moving air. But you're now using 2 big fans instead of these 12 tiny fans, right? And then the rest of it remains the same. So the number of heat sinks, right? And so now if you take that out to the rack level, right, we've replaced 430 fans with less than 100 fans in the other system. So we've achieved one of the key things I mentioned in my kind of pre-summary at the beginning, where we have less components, which means less cost, right? These 2 fans cost less than those 12 little tiny fans. They are more efficient. They move more air for a given number of electrons, and there's less of them. So the failure profile is superior, right? So simply by rethinking the form factor of how these are delivered, we've managed to make an optimization, right? So let me kind of allude to one more aspect, before I move on to kind of a high level summary. So we don't run data centers on potato juice or potato skins, but peeling a different layer of power. So there's a similar analogous advantage to less power supplies. So that 1U server at the back also had 2 1U power supplies. They had to be redundant again. So there was 80 power supplies in a rack. In a OCP design, we centralized that power across a number of nodes. So we have a larger set of power supply, a smaller set of larger power supplies. So again, we have less components, we have higher efficiency, and we're less waste as we transfer power into these systems. And it all comes by just rethinking the form factor of how we do these designs, right? We lose a little bit in terms of interoperability, but we gain a huge amount in efficiency, right? And the reason, the primary reason that they did these thin servers rather than the wide pizza boxes is we're able to fit 3 servers in the space of 2. So what we see on the bottom here is a traditional, what is generally referred to as a 19-inch rack. So all racks are 24 inches. Actually, the outer dimensions of a rack is 24 inches. 19 inches refers to the distance between the rails inside the server. What OCP did is it took an additional 2 inches from that rail distance. So made the rails, we had to basically remove the rails, made it simpler, so that we have 21 inches between the posts. And what that allows us to do when we're doing one of these 2U servers, which was the kind of standard component of so much of our computing today, or in the time frame that these systems were designed, we're able to fit 3 2U servers across in the same space as you could do 2 pizza boxes. So we'd be able to put 50% more servers, 3 instead of 2, by just rethinking a bit about the way that the traditional design techniques were done, right? And so now imagine just the same concept applied over and over again at all the different scale levels of computing. So a similar design philosophy was applied to the electronics inside, the electronics that manage the drives, the electronics that manage the networks themselves. We simply stripped out a lot of complexity that had crept in due to interoperability and so on over time. Here's a further innovation to take the fans even to the back wall. I'm not going to go into that. There's not enough time. So let me very briefly mention circular, and then I'll summarize. We can take questions. what we've done at IT Renew with the circular economy, we process, because of our decommissioning work with all of the, almost all of the largest hyperscale service providers, we process 40,000 to 75,000 servers per month through our facilities. And what we do is we draw from that pool of material to create our Sesame rack integrated solutions, to create, that's last 2 years old, that's my product division. We're also extracting some of those components to build edge computing devices, so smaller scale computing, not quite full racks, maybe 8, 10, 12 nodes in different form factors, right? And then we have some other more traditional ways to reuse some of that componentry. But the important thing is that we're drawing from a material flow that already exists in the world. So rather than having a new motherboard manufactured in order to support your computing, we're providing a second life and sometimes a third life to motherboards and compute components that already exist. Massive reduction in carbon footprint, massive savings in terms of cost, right? So this is additive on top of the benefits of operating in the open. We're also able to do this acceleration by the way that we source our components, and we're able to feed that back in a much more sustainable way to the entire ecosystem, right? So I'm gonna skip the progress slide. So this is a slide I put together, kind of my first slide that I made back in grad school of high scale computing and what high scale computing looks like today. So I'll let you look at the factors of improvement over time. Just briefly show a picture. This is rack integrated. I've already shown. On the left-hand side is what we call our Discovery Fast Start appliance, where we make 4 or 5 hyperscale computing nodes. So those same nodes that we integrate into the racks, available in a deskside unit. So this is an example of the type of edge computing reimagination that we might do. So if you're interested in a hyperscale, 100 cores, terabyte of memory, terabytes of NVMe under your desk, take a look at our products there. But it's built on that same philosophy of we can reimagine how hardware is deployed. I'm not going to go into kind of zettabytes and yottabytes. As I said, there's more stories. Take a look on our website for some more details about the circular economy. Also, some more details of what we've done with some Kubernetes stacks, my serverless to serverless talk. But otherwise, I want to kind of wind down and take a set of questions. Jerry?
Okay, thank you, Eric, for a wonderful presentation. Does anybody have any questions at all? Please feel free to put them in the Q&A section at the bottom of your screen, and we'll get to as many as we can before the end of the hour. Anyone at all?
Yeah, so I see that, Jay, I pulled up the Q&A, so I see John Laban is also involved in the Open Compute Initiative, and he's making the point that SK Telecom has experienced 50% less energy consumption using the OCP model. So there's definitely, I didn't belabor that, but there are definitely efficiency gains in many parts of the chain, and this is not uncommon. So it's not uncommon to talk about 25, 30, 35, sometimes 50% savings in the comparable systems.
And Roberto is asking, what about internal storage solutions? How can I replace internal drives of standard rack servers?
Yeah, Roberto. So there's obviously a lot of details to answer that question. But we have, if you look at our website, if you contact me offline, we have a modest amount of storage that we can put inside the devices, inside those servers. So that 1U OCP node server, that was a Leopard design that I showed, we have 15 terabytes of NVMe flash for devices that we can put inside the server. And then we also have solutions for JBODs of HDDs, hard drives that are separated from the computing. So that's one of the innovations that you saw from the 1U, kind of rather than having the drives in the front, we've kind of segregated the drives into another section of the rack so we can focus on that serviceability. And so we have JBOD solutions with 30, 70, and 100 drives per node. So we can do up to 2 petabytes per node still this year in terms of HDD storage. So we can do very high capacity with a slight rethink of the design, but there's no compromise in terms of storage capacity.
And both John, I apologize if I'm mispronouncing your name, is asking, how do the OCP products compare to old school pizza box servers in regards to price?
Yeah, so there's a lot of pieces that go into price, of course. Some of the baseline discussion, kind of just using a new OCP server versus a traditional new server. Customers talk about maybe 20%, 25% savings, 15, 20, 25% savings. When we position our recertified products where we're not having new components built and deployed, our baseline discussion with customers is 30 to 50% savings versus traditional computing. So OCP itself, maybe 15, 20%, using our recertified model, maybe 30% plus. So happy to discuss that further offline. Obviously, there's a lot of apples to apples that has to be done, like you mentioned, but there is definitely significant savings to be had.
Okay, do we have any other questions at all? John is saying that Yahoo Japan has done comparative studies of times to replace components in OCP with the ability to change all components in less than 180 seconds.
Yeah, so that speaks to that serviceability maintenance aspect that I talk about, right? I didn't certainly, there's a lot of aspects that I could have spent more time on, but one of the philosophies of OCP was also to have toolless modification. And if you look at trying to service or trying to change out some of the components in that pizza box server, then in that OCP node, it's a very different exercise, right? You don't need fancy screwdrivers. You don't need a magnifying glass to keep the screws in place. And that was all part of the design philosophy. Again, simplification reduces cost, improves maintenance.
Okay, do we have any other questions at all?
So again, I'd encourage folks, take a look through the slides, pass it along to your hardware teams, let them know there's a lot of details here to still be had. I only barely scratched the surface of all the layers.
Eric has a question. Is OCP focused on x86 only, or is ARM included?
So there are some ARM designs for example, there's some storage systems that were built with ARM. There are AMD EPYC-based designs in OCP, and I believe that if they're not released yet, they will be released soon. There are also ARM server designs in OCP. So if they aren't released yet, they will be soon. But certainly Intel and AMD are well covered. And the switch designs and some storage system designs have been done around ARM that have been contributed. I'm not sure about kind of high thread count compute, but if they aren't yet, then they certainly will be soon.
Okay, we only have a minute left. Does anybody have any questions at all? Sean is asking about open acceleration modules.
Yep, so I didn't spend any time on this. There are also initiatives on hardware acceleration, so GPU and FPGA type acceleration. Those are also being standardized over the last year. There's a number of groups that are active in OCP. So anyone interested in accelerated computing, there is also a hardware group or an OCP subgroup for that.
All right, well, thank you, Eric, so much for a great presentation and QA facilitation. That is all the questions we have time for today. Thank you all for joining us. As I said before, the webinar recording and slides will be online later today. We're looking forward to seeing you at a future CNCF webinar. Have a wonderful day. Thank you again, everyone.
Thanks, everybody.